Boiling water is easy. Designing an electric kettle is much more complicated. Electric kettles are usually made from nickel and chromium-plated copper, stainless steel or aluminium. The metal is formed into shape by a series of pressings. The body of the kettle is shaped by deep drawing, which needs a large press. In the design of the shape, care has to be taken to avoid cracking round the base. A hole has to be punched in the top of the dome for the lid. The metal for the spout cut from a blank and then bent into shape. Another pressing forms the base, and this is placed into the trimmed dome ready for soldering. A silver solder is used. Any other metal, such as lead, could poison the water in the kettle. The spout is silver soldered as well. The flux used in the soldering is highly corrosive. The operators wear special glasses to protect their eyes and industrial rubber gloves. Afterwards, the kettles are thoroughly washed to remove any traces of solder flux. Selling kettles is a highly competitive business. They've got to look good, so they're polished both automatically and finally by hand. Compared with other mass-produced kitchen articles, a kettle involves a lot of hand assembly, so the operation is fairly time-consuming. This company were trying to cut the cost of production by designing a kettle whose body could be formed in one single pressing. They wanted to produce a kettle which was pleasing to the eye and cheaper to make. An important part of the package was the price. The lower the better. Various shapes were carved out of wood, basic evaluation. They were examined by the marketing department to decide what the best-looking design was. Finally, a prototype was made out of stainless steel to see how easily it could be formed in an automatic press.
You can stop work on that, Alan. I think we've got a problem. We've got a lot of splitting on the kettle. The toolmaker thinks that it won't run as a production unit. Interstage annealing doesn't seem to be curing the problem, and the spouts are splitting at the front, and also again there's very severe splitting at the back. It would be
that's the big problem, the area at the back here.
Yeah, definitely.
It's just too much for the material all in one hit.
And we're having to do the spout in a second operation, which is also difficult, and we're wasting a lot of material on the trimming. So I think we've got to look at this in a different light altogether.
Get away from pressing.
Well, I think we've got to get away from this type of pressing. Just isn't on.
So, reluctantly, it was agreed that stainless steel was technically and financially unsuitable for mass production. The search was on for another material. Other metals were likely to be as unsuitable as stainless steel. So the designers turned to plastics. It was relatively easy to produce a tool that could be used on an injection molding machine, but finding the right plastic was more difficult. It had to be able to hold boiling water with distorting and withstand rough handling in the kitchen without cracking or springing leaks. It also had to have a high-quality finish. A plastic was found which seemed to fit the bill. A simplified body was designed which could incorporate all the gadgetry. The housing for the wiring could be recessed into the body, reducing the risk of it being knocked about and damaged. A meter shows the amount of water in the kettle. No need with this for a removable lid, as the kettle is filled with the spout. All this makes the kettle much safer to use. There's less likelihood of spilling boiling water or getting burnt by steam coming out of the lid. Because the body is made of plastic, a metal plate has to be inserted in the bottom of the kettle to isolate the plastic from the heating element. A ball float operating a switch was also inserted to prevent the element from heating unless it was covered with water. This will protect the plastic from excessive heat. But these extras were more than offset by the attractiveness of the design. There was saving too. There were fewer metal pressings, and parts could be assembled using simple high-frequency welding techniques and self-tapping screws. The new product was put through a number of trials. Here the technician is testing the kettle for its insulation resistance, one of a number of tests insisted on by the British Electrical Approval Board. As part of the endurance trials, full kettles were boiled 50,000 times. After every conceivable laboratory test had been done, the kettles were set out for the most critical testing of all, everyday use in a score of homes. These field trials, they're called, are crucial. Consumers are notoriously all thumbs, and if there are any faults in the new kettle, they'll soon show up in the kitchen. One thing real people do, as opposed to designers, is to spill things on their kettles. Anything. Boiling fat, bleach, food. And then they wipe them clean with dirty cloths. Well, that wouldn't do a metal kettle much harm, but fats and oils can weaken and discolor some plastics. And that's exactly what happened. The kettles began to turn yellow, and they started cracking. It was back to the drawing board, and another polymer, resistant to fats and oil, was used for the body instead. This time the kettle withstood all the ill treatment it got in the kitchen. This elegant kettle is now a bestseller, made out of plastic, but originally conceived in stainless steel. Using plastic enabled the designer to change the look of the kettle radically. Plastic was not just easier to mold, but it had virtues of its own. With its poor thermal conductivity, you can put your hand on it even when the water's boiling and not get burnt. Important that when there are children in the kitchen. even the smallest of changes in a product can have far-reaching consequences. This diesel engine forklift truck and its potential pollution problem led to a significant breakthrough in engine design for one of Britain's leading diesel manufacturers. The invisible exhaust gases belching out into the factory are a potential health hazard. During the last decade, the Americans have tightened controls on exhaust emission, and if we were to export successfully to the States, we had to conform. So in 1974, research began to find out how possibly harmful exhaust fumes could be reduced. It became increasingly clear that the problem must be tackled right in the heart of the engine, in the combustion chamber. Unlike a petrol engine, a diesel has no ignition circuit. The piston compresses the air in the cylinder and fuel is then injected. As the air is compressed, it becomes hot, and at the critical moment, the fuel, mixed with the hot air, spontaneously combusts. The exhaust gases are a mixture of completely burnt fuel and partially burnt fuel. And it's this partially burnt fuel that is potentially harmful. To achieve maximum combustion, the fuel has to be well mixed with the air before combustion takes place. The efficiency of this mixing is largely determined by the design of piston. The normal piston looks like this. It contains a bowl which creates turbulence. When the fuel injected, the turbulence mixes it with the air, but it doesn't do it very efficiently. If you alter the shape of the bowl, would that help? The science of what happens in the cylinder as the piston compresses is complex, and without using advanced computer techniques, not capable of precise modeling or prediction. A lot of time has to be spent designing new piston shapes and testing them out in practice.
There's no carbon packing in there, there's not a lot of wear at all. But I wouldn't mind betting that rail is coming loose.
A number of different shapes were tried out. All these had to be run in engines to see what happened. The performance of the engine was tested and the exhaust gases analyzed. Eventually, a shape was found that seemed to be an improvement on all the others. This shape, later called the squish lip, created enough air turbulence to ensure that all the fuel was burnt completely. This is a computer simulation of the airflow in a cylinder with a conventional piston. On the right is a representation of half piston pushing along the cylinder. The vector arrows show the direction and force of the air. Turbulence doesn't really build up significantly until the crankshaft has turned through 130 degrees. It then gradually builds up to the top of the piston cycle at 180 degrees. If fuel is injected before then, there isn't sufficient turbulence to mix it efficiently. But in the squish lip piston, turbulence builds up much sooner. By around 110 degrees, it becomes quite turbulent in the bowl, and the build-up intensifies dramatically during the cycle. By the time the fuel is injected, it mixes with the air quickly and efficiently. Choosing the right shape was, however, only the beginning. A great deal of research work had yet to be done by the piston manufacturer to find the right metal from which to build piston and the best techniques to use so that the piston should have as long a working life as possible. As far as the mixing of the air and fuel went, the best results came from a bowl with an acute angle to the lip. But with that shape, heat built up around the lip, and using conventional aluminium, the heat was not easy to dissipate. A number of alternatives were tried. Bonding a layer of special toughened aluminium to the top of the cylinder didn't help appreciably. The best results came from inserting a ring of beryllium copper into the casting. It was held in place with steel pins. This was dramatically successful. The heat was dissipated quickly, and the piston had a long life. But there's always a snag. It cost far too much to make. Eventually a compromise was reached. Angle of the lip was increased so that the piston could be made in a single casting aluminium. Piston is die cast. First, a cast iron ring is dipped in melted aluminium. The aluminium coats the ring and also raises its temperature, enabling it to form a better bond with the casting. The ring provides a strong seating for the piston rings. It's placed in the die, which is then closed. The die has a large riser. Any bubbles which could make the casting porous rise to the top of the riser out of harm's way. The casting is cooled. The bowl of the piston is machined and not cast, again, to avoid the risk of porosity. The only feasible way of cutting a consistent shape again and again and maintaining the close tolerances required is to use a computer numeric controlled machine tool. Normally, of course, a coolant would be placed on the cutting edge, but while we were filming this sequence, it turned off so that we could see the operation more clearly. The tools had to be specially developed so that they could cut in any position and at any angle. The pistons worked well, but that's not the end of the story. Something very unexpected and exciting happened. While the new piston did its required job and delivered clean exhaust gases, it was found that more fuel could be injected and the power of the engine increased dramatically, 20% more than would be produced from a conventional engine of the same size. This increase of power-weight ratio gave the company a healthy lead over its competitors, particularly in the highly competitive and specialized field of marine engines. Whatever the size of a boat, the less space an engine takes up, the better, and ideally, it should be as light as possible. Then there came yet another refinement. Engines tend to be placed in confined spaces, and to lessen the risk of fire, the parts to get hot have to be heavily lagged. The company decided to see what they could do to reduce need for such lagging. They came up with what they called a multi-cooler, an integral unit containing the seawater-freshwater heat exchanger, a cooling system which would also cool the exhaust while still allowing it to run a turbocharger. The first prototype proved that the idea was valid, but there was a problem. The air entering the multi-cooler began to be heated as soon as it entered the system. By the time it got to the engine air intake, it was too hot. The remedy was an air gap was designed into the casting to insulate the airflow from the rest of the system. Then another problem. The face where the turbocharger was fixed was found to leak. Flat surfaces are all difficult to machine perfectly flat. Flanges at the joint face reduce the error needing perfect machining. The multi-cooler was tested in the workshops. As boats are never still, except when it's dead calm, the engine and the cooler were tested on a bed that could be moved to simulate the buffeting of a boat at sea. They even tested the end running upside down, something that might happen in a lifeboat with a built-in capacity for self-righting. There were exhaustive sea trials and high-speed performance tests. The job of actually making the multi-cooler had been given to a specialist casting company. The metal chosen was aluminium. Anything else would have been far too heavy or far too expensive. Because of the large number of channels of casting, it wasn't an easy job to do, and it called for an unusually large number of sand cores, which had to be very carefully positioned. The casting also involved long runs of thin sections, which encouraged hot shortness, metal cooling before running through the whole section. Either misalignment of cores or hot shortness caused wall failure in several of the prototype castings. Eventually, the core alignment was perfected, and by increasing the number of feeders, the company was able to produce successful castings. The finished multi-cooler was given yet more sea trials in all weathers and sea conditions. The system proved to be highly successful, and the result of all this painstaking, often routine work proved of considerable benefit to the company. Design involves the bringing together of many disciplines and techniques, and many skills. It's very much a team effort. Complex engineering involved, advanced metallurgy, the artistry of both mind and eye. The aim always to improve, make things better than ever before.